All right, let's dive in. Today we're tackling something pretty mind-bending. Quantum reservoir computing. QRC for short.
Yeah, it's definitely a mouthful.
But it's also super fascinating, right? This idea of using, quantum mechanics to do machine learning.
It is. The possibilities are huge.
Exactly. And to guide us through this, we've got Jurgo Schneppet's essay, QRC, Quantum Reservoir Computing for Intelligent System. It's a deep dive, no pun intended.
Lots to unpack there.
Definitely. So maybe before we get into the nitty-gritty, could you give us a quick Quantum Mechanics 101, just a refresher on the core principles?
Yeah.
For anyone who hasn't thought about superposition in a while.
Sure. Well, first off, gotta remember, quantum systems, totally different beasts than the classical systems we're used to.
Right. Different rules.
Totally. So take qubits, right? The building blocks of quantum computers. A qubit can be in multiple states at once.
Superposition.
Exactly. It's not like a light switch. On or off. More like, I don't know, a dimmer switch.
Okay, I see. So many positions at the same time.
Right. And then there's entanglement.
Oh, yeah, entanglement. Always a brain twister.
It really is. You get two or more of these qubits linked together.
Even if they're miles apart, right?
Yeah, doesn't matter. They're connected. Like, whatever happens to one instantly affects the others.
Spooky action at a distance or something like that.
Something like that, yeah. And that connection, that entanglement, it's a big part of what makes quantum computing so powerful, potentially.
Okay, so we've got these weird quantum properties.
Yeah.
How does this all tie into reservoir computing?
Well, first, let's talk about what reservoir computing is. Think of it as a network, interconnected nodes, like a web, maybe.
Okay, got a web in my head.
And this web, that's your reservoir. It's designed to process information. But the thing is, you don't program the reservoir itself.
It's kind of doing its own thing.
Exactly. The complexity comes from how it's structured, all those connections, and then you've got the simple readout layer.
Sitting on top of the web.
Right. And it learns to interpret the output from the reservoir.
So we don't need to know exactly what's going on in that web, just how to read the signals it sends out.
You got it. It's super efficient and really robust. Great for tough problems, especially ones that change over time, like a time series.
Okay, that makes sense. But hold on, we started with quantum mechanics. Where does that come back in?
Here's where it gets really cool. In quantum reservoir computing, the quantum system is the reservoir.
Whoa. Wait, so those qubits and their weird behavior, that's our web.
Exactly. All that superposition, entanglement, that natural quantum dynamics, that's doing the information processing.
So we're just letting the quantum system do what it does best, be all chaotic and weird, and then
you train the simple readout layer to make sense of it all.
So we're harnessing the chaos. I like it. But, what does this actually look like in practice? What kind of quantum systems are we talking about?
Well, Schneppet talks about a few different platforms that researchers are working with. There are superconducting qubits, for example.
Those rely on superconductivity to keep their quantum states stable. Right.
Yeah, exactly. Then you've got photonic systems. Using photons, particles of light, they carry the information.
Light is data. Cool. Anything else?
Even systems using trapped ions.
Trapped ions.
Yeah, like individual atoms.
Yeah.
Held in place and manipulated with lasers. Super precise stuff.
Okay, so lots of different ways to build this quantum reservoir. But I'm guessing coherence and entanglement still matter, right?
They're essential. Coherence is all about how long a qubit can hold on to its quantum state before it decoheres, before it loses those quantum properties.
So the longer it stays coherent, the more we can do with it.
Exactly. More complex computations.
And entanglement is what lets those qubits work together, right? Kind of amplifies their power.
Precisely. More entanglement, more power.
But like we were saying, keeping those qubits coherent, that's got to be tough. It's quantum mechanics. It's all so delicate.
Yeah, decoherence is a huge challenge. It's like trying to build a house of cards in a windstorm.
Oh, I get it. The longer you go, the more likely it is to all fall apart.
Exactly. Managing that along with entanglement, that's key to making QRC work.
So it sounds like we've got the basic picture of QRC now. Quantum weirdness doing the heavy lifting, readout layer, making sense of it all, and this constant battle against decoherence. But okay, let's get to the good stuff. What can we actually do with this technology? Schneppet mentions quite a few potential applications.
Yeah, he does. And some of them are, pretty mind-blowing. Like, let's start with machine learning and AI.
Okay, so how could QRC actually change the AI game?
Well, one of the big ones is predicting time series data, stock prices, weather patterns, things like that. Complex systems that are hard to predict with classical methods.
So instead of our usual algorithms, we could use these quantum reservoirs to find patterns, maybe even predict the future.
In a way, yeah. Quantum systems explore way more possibilities than classical computers. So QRC could be a game changer for forecasting and risk management. And it's not just finance. Think about image and speech processing.
Oh, right. Snephat mentions those too. Like, how could QRC actually improve those?
Well, imagine medical imaging. Being able to spot tiny abnormalities in scans, things the human eye might miss.
That's incredible, like catching diseases earlier, potentially.
Exactly. Or in speech recognition. Systems that are way more accurate, adapt to different accents, languages, stuff that really trips up current tech.
Yeah, it's amazing how much even small differences can throw off those systems. So it sounds like QRC isn't just about speed, it's about seeing things differently.
That's a good way to put it. It's about recognizing patterns, subtle ones, that classical computers might completely miss.
And that leads us to optimization problems, right?
Yeah, another big one.
So remind me, what exactly are those again?
Optimization problems. It's all about finding the best solution, the absolute best, out of a ton of possibilities.
Like finding the fastest route for deliveries, or figuring out how to use resources most efficiently on a project.
Exactly. Stuff like that. But these problems can get really tough for classical computers to handle, especially as the number of variables grows, It gets messy.
I can imagine. So how does QRC help with that?
Well, it's that whole exploring multiple possibilities at once thing. Quantum systems can explore so many options simultaneously. It's like, a massive parallel search.
Okay, that makes sense. So it could cut down the time it takes to find solutions.
Potentially, yeah. And Snephat even suggests that QRC could tackle NP-hard problems.
NP-hard?
Yeah, they're like this class of problems that are notoriously hard for classical algorithms, like really, really hard.
So if QRC could crack even a few of those, it would be huge.
Huge is an understatement. We're talking major breakthroughs in logistics, finance, cryptography, all sorts of fields.
Wow. Okay, so that's all pretty impressive. But we've mostly been talking about computer science applications. Snephat also mentions QRC's potential in physics and engineering.
Right. And it gets even more interesting there, I think. One of the most exciting possibilities is using QRC to simulate other quantum systems.
Simulating other quantum systems, how does that work?
Well, imagine being able to design new materials from scratch. By actually simulating their quantum properties, you could create materials with specific properties for things like solar cells or batteries, or even quantum computers themselves.
Wait, so we could use QRC to build better quantum computers?
It's possible, yeah. It's kind of a mind-bending loop, right?
It is. And what about drug discovery? Could QRC help there too?
Absolutely. Think about simulating how different molecules interact at the quantum level. That could completely change how we develop new drugs and therapies.
Wow. It could also help us understand, complex biological processes, right? Things that are just too difficult to model with classical computers.
Yeah, we could get a much deeper understanding of how things work at a fundamental level.
So it's not just about building new things, it's about understanding the world around us in a completely new way.
Exactly. And there's also this idea of using QRC to control complex systems in real time.
Oh, right. Snephat mentions that too. But what does that actually mean?
Well, think about things like managing the power grid, optimizing traffic flow in cities, controlling industrial processes. QRC could potentially help us monitor and adjust these systems with, incredible precision and efficiency.
Okay, I see. So QRC could be this powerful tool for managing all sorts of complex systems. But let's be real for a second. As exciting as all this sounds, there are still major challenges, right? We've already talked about decoherence.
Yeah, decoherence is a big one. And then there's just the fact that current quantum hardware is still pretty limited.
Limited how?
Well, the number of qubits we can control, their coherence times, how accurately we can manipulate them, it's all still pretty early stage. It's like trying to build a skyscraper with, toothpicks or something.
Yeah, I get it. We need better tools before we can really unlock the full potential of QRC. But Snephat does point out that the field is moving fast.
Oh yeah, definitely. New qubit designs are coming out all the time. Error correction techniques are getting better, and researchers are finding more efficient ways to control these quantum systems. It's a real collaborative effort. Physicists, computer scientists, engineers, everyone's pushing the boundaries.
So where do we go from here? QRC is a young field, lots of potential, but also lots of hurdles. What's the big takeaway for our listeners? It's kind of like we're at this turning point, right? Quantum reservoir computing, it's not just about making computers faster. It's a whole different way of thinking about what computers can even do.
Yeah, totally. Snephat makes a good point about that. We're really just starting to scratch the surface of what QRC might be capable of. So many challenges, but the payoff could be huge.
It's like we're on the verge of something massive, This tech, it could change how we understand the universe,
Yeah.
how we solve everyday problems. It's pretty wild to think about.
It really is. And the coolest part is we're not just watching this happen, we're part of the conversation, figuring out what this technology means for our future.
Absolutely. So to wrap things up, I want to leave our listeners with something to think about. Imagine QRC really does unlock the power of quantum mechanics. What problem would you want it to solve?
That's a good one. With that kind of power, the possibilities are endless. And like Schneeplatt says in his essay, those possibilities, they might be closer than we think.
Well, on that note, thanks for joining us on this deep dive into quantum reservoir computing. Until next time, keep exploring, keep learning, and keep asking those big questions.